Hi there, I'm Christopher Worst and welcome to the third video in the Homework 2 playlist for material energy balance. This video is going over question 3, which is on the screen right here. It says, calculate and plot PV isotherms of water using the SRK equation of state. So, to do that, we're going to be creating a co-laboratory script that calculates and plots the isotherms. So, to remind you, an isotherm is these lines here that go through, that calculate temperatures based off the volume and pressure. A critical isotherm is the one that goes to the critical point. The rest can either be above or below it. This area right here is an area where the theoretical temperature can be calculated, but the actual temperature cannot be obtained because there's a mix of liquid and gas vapor here that prevents you from doing so experimentally. So, to do this, we are going to be using the generic equation of state, and the values given in the SRK line here of this equation of state. So, we know that from earlier videos, video 2 specifically, pressure equals R times the temperature divided by volume minus B. Now B, this wasn't explained in previous videos, but B is the excluded volume for other particles that you're not looking for, such as air particles or something like that. Minus A divided by volume plus epsilon B times volume plus sigma B. So B, the equation for B is given here. It is omega times R times the critical temperature divided by the critical pressure. A is given as the critical temperature. A at the critical temperature is given here. However, it's not what we're going to be using. We're going to be using this value here. So A is equal to psi times alpha, the alpha of the residual temperature times omega times R squared times critical temperature squared divided by critical pressure. TR is the temperature divided by the critical temperature. So we also have here alpha, an equation for alpha given for the SRK equation of state, value for sigma, value for epsilon, value for omega, value for psi, etc. So we're going to be using those to create a code for this. So let's begin. So first things first, I want to import the ChemTool script that our teacher wrote up for use in this code. So we're going to be using the command git clone double dash depth is 1, and control V, and I want to do depth 1 to make this the first thing that pops up. This is connecting to the Wi-Fi, initializing connected, cloning, and we're good. Now I want to import everything that I need. So I need to import first sys for system, and I'm going to use sys.path.insert for the first thing, so it goes immediately to that, and then what do I want? I want \che content, another \che tools, and I need this to be in parentheses, so it's a string. Next, we need to import numerical Python, so numpy as np. I need to import from scientific Python, from scipy, import scipy.optimize. I will need root for a later equation, for a later homework, for one of the next questions. I will also need plotly, so from plotly subplots import make subplots. I'll need to import plotly.io as PO, so I can use that as both shorthand and to make the actual figures that we're going to be using. For that end, po.templates.default should equal plotly_dark. Oops. I need, because we're going to be inputting the values for the critical temperature and critical pressure of water, I need to import tools.che as che. And finally, I need to put the R value up here. I don't really need to put the R value up here, but it helps to make sure that it's easy, it's out of the way, that way it's there. So R, the rate equation, the rate constant is 8.314, shift enter. Okay, everyone's good, everything's good there. So what do we need? Well, we want to create critical isotherms. We need to create isotherms, so we need the pressure. So we need to make this equation. So we're going to need B, we're going to need A, and we're going to need epsilon and sigma. So we're going to make a function, define, we'll call the function cubic A, B, E, and S, because that's what we're finding. So let's start with what we're returning. Return A, B, E, and S. Nope. Now we need to actually make A, B, E, and S. So we have A is equal to, well, what is A equal to? Let's go over here. A is equal to psi times, that is alpha times R squared, alpha times R squared times critical temperature. So we're going to need to input P equals CHE dot props of water, and I also need brackets here. So this will input the chemical properties of water. This is a function here that I can use to call the critical temperature and the critical pressure. Shift enter to make that work. Good. That error there is just saying that's on the computer, not on the cloud, which is fine. So we want P times, P dot TC for critical temperature. I want that squared. I'm going to put this in parentheses here. And then this should be divided by the critical pressure. So P dot PC, critical pressure. Okay, now we need B. B is equal to omega times R times, so omega times R times P dot TC for critical temperature, as well as divided by critical pressure, so P dot PC. Okay, we have A and B, but we're missing omega, psi, and alpha, as well as E and S. So let's begin with omega. Omega is equal to, and in this case, now you notice that we have multiple values here. It is possible to create libraries in Python to input all of these values and then determine what equation of state we want in the actual code, but we're not going to be doing that simply because it's not necessary for the assignment. I may come back and do it later as I learn more and become more comfortable with Python to update it, so this video may get changed a little bit down the line, but just know that it is possible, and in future assignments, libraries will become have a much bigger role, and at about that point is probably when I'll come back and, at the very least, I may just add on to this and say, hey, here's how you do this to make it all work correctly. or to make it a little bit more usable in a more general sense. But at the very least, omega here for the SRK equation, the one we're looking for, is 0.08664. So 0.08664. By the way, I need temperature here. Nope. I just need a temperature. There. That is the thing that is coming in to, that is our initial guess for a temperature so that we can use it for values later, specifically to find TR. So we're also going to do psi, because that is another fixed value. So psi is equal to, here, SRK, 0.42748. 0.42748. Next, let's find alpha. So alpha is the larger equation. It's down here. So these lowercase omega values are, like critical pressure and critical temperature, they are values specific to the compound. So we're going to be using the water script. We also need TR here, so let's find TR above it. TR is equal to temperature divided by critical temperature, so P dot Tc. Now we can find alpha, so alpha is equal to parentheses 1 plus parentheses 0.480 plus 1.574 times P dot W plus minus 0.176 minus 0.176 times P dot W, also going to add one more squared here. So there, good. And this is going to be times 1 minus TR squared. So, and just to make sure that this is, the parentheses are correct, I'm going to just do a quick count. So 1, 2, 3, 4, 3, 2, 1, 2, 1, 0. Okay, so all of our parentheses are closed. We're good there. So alpha should be finished being written. Oh, and this shouldn't be 1/2. This should be 0.5. Yes, and then this should be squared. All of this squared. Yes. And misspelling here. There. Now the yellow line underneath, alpha goes away, meaning it's been equated. So, epsilon or E, value given here is 0. And then sigma or S, the value given for it is 1. Okay. Everything is written out here. Let's shift enter just to make sure. And we're going to, let's do cubic, ABES, let's call it 100 Kelvin. That looks about right from values given in class as well as just a general first look. So it looks like this function at the very least is correct. So now that we have all of these values, we need the pressure. So let's find the pressure. So we're going to define another function. So we'll call it cubic P for cubic pressure, and what we want is again the temperature. We also want the volume. So lowercase v. There we go. Enter. Oh, nope. Colon to close it. There. Now our equation, now our function is defined. We have the volume here, the temperature here. Those are our two guesses. So P is equal to, oh, actually no, we need to unpack. So A, B, E, and S is equal to cubic A, B, E, and S T with the value of T. So now that we've unpacked this from this equation, from this function, we can now find P. P is equal to, or you can just simply return R times temperature divided by R times temperature divided by V minus B. So volume minus B minus A divided by another parentheses V plus epsilon times B. Good. And then another division sign just to say that A is divided by this, then divided by another. So V plus sigma times B. Good, good, good. So I'm going to space these out just to make them look better. Kind of group them together. There. That looks better. Shift Enter. So if I do cubic pressure, say a volume of 1 and a temperature of 100, Shift Enter, which seems about right. So we're good there. Now we need to plot the isotherms. So we're going to need to create a plot, but obviously we need volumes and we need volume guesses as well as T guesses, since we need pressure guesses as well as volume guesses to create the plot. And then we're going to be picking temperatures and making a bunch of temperatures to make many different lines, many different isotherms for it. So in order to create the volume expanse, we need to define B once outside of the function. So I'm just going to copy and paste this. Copy. And what is the value for omega? 0.08664, 0.08664. Control V, paste. Now we have our B value, our excluded volume value. So now we need V. So V equals, what do we want for V? Well, if V is the x-axis, usually we would use linear space to get these correctly spaced and to make it look nice and neat. So we'll do that. np.linspace, let's try 1.01 times b. Array stop, let's start -2 as well as 100. Call it there. So we have that given. We have a general starting point for our V value and B value. Our B value is listed here. So now we want to create a bunch of values for T. So we're going to use a for loop. So for T in range. Where should we start? Start at 275. Go to 800 at increments of 25. Sounds about right to me. Colon enter. Now we need to create pressures. So pressure is equal to cubic P at what volume? V. What temperature? T. We have that. So we have that value. We have the pressure value here, but now we need to actually create plots for it. So do that. Figure is just going to be equal to, what is it? PO dot make subplots here. Okay. Now we're able to fig.add scatter to make the plots. We're going to make the individual lines. So x is going to be equal to, well, x is equal to v, so x is going to be equal to v. And we know that y is equal to the pressure. We're going to make the mode equal to lines because it looks better that way. And that looks about right for it. So we have, now that we have that to increment ranges and make different values for t, we want to add here. So let's just try Shift Enter. po.make subplots. Plotly.io has no. Let's try just fig equals make subplots. Shift Enter. That's better. It didn't make a subplot. Let's try updating the y-axis. That might be an important thing. So fig dot update y-axis range equals negative 100 E6. Call it to 100 E6. Seems arbitrarily chosen, but okay. There, we now have a graph, but that does not look right. But you can see that there are indeed different values for it. So at the very least, we have indeed done our job of collecting these. So, well, if linspace doesn't work, let's try, or linspace doesn't work because this is going backwards. Well, if linspace doesn't work, there's another type of spacing that might work. Let's try log space. Now, log space is interesting because it takes these values and adds them to, if the log of something is 10 to that power. So this means that log space takes this value and puts it as the power of 10. So negative 2 will be a power of 10. 1.01 times b will be a power of 10. To that end, we need to np.log10 this value so that it actually starts at this value here and then goes to this 10 to the negative 2, which is 1 over 100, which is 0.01. So try that, Shift Enter. That looks much better, although this value here, this x-axis still looks a little bit off, but this spread looks much better. So next we're going to update the x-axis in a similar way that we updated the y-axis, except instead of a range, we're going to be updating it to, is it mode or type? Let's try type. Let's try mode first. Mode equal to log. Shift Enter? No. Okay, I don't need that. X. Try type. Oh yeah, that looks much better. Wow, this definitely looks much better. So we have all of these traces. Well, I don't want to call them traces, so I'm going to name these lines as the last thing we do for this homework, just for a mix of fun and organization. So name is equal to f. So f is function. That means I can input a function and it will change. So it is going to be temperature as brackets Kelvin. Now Shift Enter. Look, now you have 275K all the way down to if I can do this without scrolling, 275K to 775K. You have many different values here. And just for fun, you could split it across and see that it does, as it goes on, gets closer and closer, as one might expect if this value of this plot were to be extended out even further. So I'm going to unzoom out. We have here our plot of individual isotherms and individual values, and with that, question 3 is finished. Thank you very much for watching. I hope you have a wonderful day, and part 4 will be going even further beyond this to use some of these equations to find the specific volume values for the cubic equation of state that we found earlier in question 2.